Okay, I'm going to go over a couple problems to help us review for our quiz on Introduction to Probability. So this first question says, what is the sample space for flipping a coin then rolling a dice? So I'm going to flip a coin and then roll a dice. So if we think about it, when we flip a coin, there are basically two things we can get. We can get heads or we can get tails. And when I roll a dice, I can get one of 6 outcomes. 1, 2, 3, 4, 5, or 6. So when I'm looking for the sample space, I'm looking for basically all combinations. So what I could do is I could get a head and then roll a 1. So we'll call it H1. I could get a head and get a 2. I could get a head and get a 3. I can get a head and a 4, a head and a 5, a head and a 6. So those are all the ones that have a head. I could also, of course, get the tail and get all those corresponding dice as well. So T1, T2, T3, T4, T5, T6. I think I put 2 T3s on there, so let's erase one of those. So we have 12 different items in the sample space. Once you have the sample space, this actually it becomes really neat to do these problems. So in question 2 it says, in the example above, what's the probability of flipping a head and rolling an odd number? Well, we know there are a total of 12 outcomes, so we want to just really figure out how many of these outcomes have both a head and an odd number. Okay, so it has to have both because it has the word and. So if I go and look at all these, how many of them have a head and an odd number? Well, that would be the H and 1, the H and 3, and the H and 5. Those are the only ones where I have a head and I have an odd number. So there's 3 of those outcomes. So we have 3 out of 12, which of course reduces to 1/4. So there's a 1 out of 4 chance of rolling a head and an odd number at the same time. Okay, let's look at another problem. We have a dice being rolled, and then the spinner below is spun, and we want to find the following. What is the sample space for the event above? And then we have some, obviously, questions about probability. So this will be a pretty large sample space because we have lots of letters. We have A through H. So we're going to get a dice roll, which has, of course, 6 outcomes. And then you're also going to get one of these spinner values. So if you think of what the sample space is, we could get a 1. And then after we get a 1, we could get a 1A, a 1B, 1C, 1D, 1E, 1F, 1G, 1H. So you could get a 1 in any of those values. And of course, we could also have gotten a 2. We could get a 2 for any of these. So if we get a 2 for the dice, we could still get any of these vowels. AB, or A, B, C, D, E, F, G, or H. And really it's the same thing. We could get a bunch of 3s with the corresponding letters, a bunch of 4s with the corresponding letters, and of course 5s and 6s. So we look at these, we have 8 in each column, and there are 6 columns, so we have 48 different values. So there's 48 in the sample space, and they are listed to the right. So we have a couple of questions. The first one says, what is the probability that we roll the dice and spin the spinner, and we get an even number and a vowel? Okay? Well, I can eliminate all of this row, because that doesn't have an even number, and I can eliminate all the 3s and all the 5s, because those all have an odd number. So I want an even number and a vowel. So I just look at the rows that have the 2s, the 4s, and the 6s. So 2 and A is an even and a vowel. 2 and E is a vowel, and those are the only vowels in our problem. We could also do the same with 4, 4A, and 4E, and of course 6A and 6E. So those are the only 6 outcomes that would have a vowel and an even number. So our probability would of course be 6 out of 48, which both divide by 6, so we can reduce that to 1/8. Now let's see how this is different if we say it is a probability of an even number or a vowel. So all the ones we have circled in red would still be fine. But if you think about it, if I want an even number or a vowel, I just need one. Or both would still be fine. But I really just need one or the other. So if I think about 1A, that would work. And 1E would work because they have a vowel. It doesn't have to have both because it says the word or. 2A would of course still work. 2E would still of course work. But so would 2B because that was an even number. And 2D, and 2C, and 2F, and 2G, and 2H. So really all the columns with the even number would work because we have an even number is one of our criteria in our OR statement. And then the vowel part, we obviously can match up when we talk about 3A, 5A, 3E, and 5E. So if we count how many we have basically 3 full columns, which is 24. And then we have 25, 26, 27, 28, 29, 30. So we have 30 circled that have an even number or a vowel. So this would be 30 out of 48, which could reduce to 15 over 24. So there's a 15 out of 24 chance that we get an even number or a vowel. When it's both, that's fine, because we don't have to subtract them. These are obviously not mutually exclusive because there are lots of them that have even numbers and vowels. But when we're just circling from the sample space, we don't have to worry about that. So this last one says, what's the probability of not getting a 6 and not getting an H? So we want to know all the ones that have no 6 and don't have an H. So the only one that has both of these would be 6 and H. So this one, the 6 and H, has both of these. So every other one has not a 6 and not an H. Doesn't say or, it says and. So they both have to be true. So really, this would be all of them except for one, so this would be 47 out of 48. All right, let's look at number 7. It says if the probability of A is equal to 0.2 and the probability of B is equal to 0.3 and the probability of A or B is 0.4, are A and B mutually exclusive? Well, our rule says they are only mutually exclusive if the probability of A plus the probability of B equals the probability of A or B. If this doesn't hold true, then they are not mutually exclusive. So A is 0.2, B is 0.3, which is equal to 0.5. That is not equal to 0.4, which is listed here, so we say these are not mutually exclusive. So those events are not mutually exclusive. They do have stuff in common. So very important to remember this formula for being mutually exclusive. If you add them together, they need to equal the OR. Okay, let's go ahead and look at 8, 9, 10, 11, which is all talking about a coin being tossed and a single card being drawn from a deck of cards. Now, if we think about this, when we flip a coin and get a card, and we're trying to list the sample space, this would be a ginormous sample space. We could have a head and an ace, a head and a 2, a head and a 3, and that could also be a heart, it could be a club, it could be a diamond. This would just be a ginormous sample space. So it's not really efficient to write all these things out and do it as we did on the previous problems. So we're going to go ahead and use our probability rules. Now if you remember our probability rules, we had the one for mutually exclusive for OR that said if they are mutually exclusive, the probability of A or B equals the probability of A plus the probability of B. We also had the problem that said if A and B are independent, probability of A and B is equal to the probability of A times probability of B. And that's if they're independent. And then our last one was our conditional probability, which said the probability of A given B is equal to the probability of A and B divided by the probability of B. So these three rules will be invaluable for us as we try to do these problems because we do not really want to write out this sample space. So the first question says, tossing a head and drawing a diamond. Now these are mutually exclusive events because if you think about heads and diamonds, there are no overlapping, or if you get a head, it doesn't necessarily mean that you're going to get less diamonds. So if I say the probability of getting a head and a diamond, well, the probability of getting a head is 1 out of 2. And the probability of a diamond is one of the suits, so that is 13 different suits, or 13 different cards, so that's 13 out of 52. So if I multiply these, I get 13 over 104, which can reduce to 1 over 8. So because they're mutually exclusive, if you get a head, that doesn't necessarily mean you lessen the chance of getting a diamond, so we can multiply them together. Now if we think about the probability of getting a head or a diamond, well, this is a little different because the probability of getting a head or a diamond, since it's an or, we're talking about being mutually exclusive. So we're saying, is there any outcomes where you can have both a head and a diamond? And the answer would be yes. There are lots of head-diamond combinations. Head, ace, diamond, head, 2 of diamonds, all these. So or means add, so I can add them together, 1 over 2, that's fine, plus a diamond, which is 13 out of 52. But if you remember, since they're not mutually exclusive, this rule does not apply. We have to subtract the overlap. So we have to think about how many of our outcomes, how many head-diamond combinations are there going to be. Now, if you think about it, there are a total of 104 outcomes because you got 52 for the heads, 52 for the tails. So we're subtracting 104. So how many of those have heads and diamonds? Would only be the ones with the diamonds with the head, so that's only 13 outcomes, so we'd be subtracting that out. So we have a half plus 13 over 52 minus 13 over 104. So I'm just going to stick this in a calculator, and that's going to give me 65 over 104. So 65 out of the 104 have a head or a diamond, one or the other. Okay, the last one says, what's the probability of tossing a head given a diamond was drawn? So if we're going to do this, this uses this rule up here that says conditional probability is the probability of both of them happening divided by the probability of B, which in this case would be a diamond. So the probability of tossing a head and a diamond is the problem we did above. That's number 9, so that's 1/8. So we'll take 1/8. And we'll divide that by the probability you get a diamond. So if you think of how many diamonds there are 13 diamonds out of 52, which reduces to 1/4. So again, if I put these in parentheses and put it in the calculator and divide, I get 1/2. So if I've gotten a diamond, so if I know I already have a diamond, you think about it, if you already have a diamond, then there's only a head attached to it or to a tail attached to it, so it really makes sense that that should be 1/2. Okay, for the next couple of questions, we are going to look at this table which talks about our feelings about college and our school that we come from. So 12 says, are the events excited about college and Olentangy mutually exclusive? And the answer would be no. And the reason why it's not mutually exclusive is because these 150 people have both these characteristics. When they're mutually exclusive, these can't happen at the same time. Because of the 150 people are both excited about college and they are from Olentangy. So that's what makes it not mutually exclusive. If they couldn't occur at the same time, Or if this was 0, then they would be mutually exclusive. Okay, so 13 says, what's the probability that the student is from Old Tangy or excited about college? So this is an or. So we know we're going to add, but since it's not mutually exclusive, we'll have to subtract the overlap. So if I think of the Old Tangy, there are 350 students from Old Tangy out of 1,000. And the excited people, there are 450 out of 1,000. But again, the problem is I've now counted these 150 people twice. So I have to subtract those out. So I'll subtract the 150 people out. So 350 plus 450 is and minus 150 is going to be 650. So this will be 650 out of 1,000, or 0.65. All right, 14 says, what's the probability they're from Old Tangy given they're excited? So remember, our bar means it's already happened. So when I see that bar and it says given they're excited, that means I'm only talking about these excited people. I already know the person is excited. Whatever comes second, that means that's already happened. So since they are it's already been determined that they're excited about school, about college, then we only have to think about, of those 450, how many are from Old Tangy? Well, that'd be just simply 150 out of 450, which reduces to 1/3. So just remember, when a table is pretty simple because you just look at which ones you have. All right, our final problem says if A and B are independent and the probability of A and B is 0.16 and the probability of A is equal to 0.2, what's the probability of B? This will take advantage of our general multiplication rule. We said if they are independent, then the probability of A times the probability of B equals the probability of A and B. So the probability of A is 0.2. The probability of B we don't know. In class we put an X, so I can put an X there as well, equals 0.16. So we're trying to figure out 0.2 times what equals 0.16. So I'll just divide both sides by 0.2. So if I use my calculator or whatever I'd like to use, 0.16 divided by 0.12 is going to be 0.80. So the probability of B is 80% because they are independent. All right, hopefully this quiz review was helpful. Let me know if you have any questions.